Right, you have to calculate the equivalent resistance of the parallel network. Well, the first thing is that this entire circuit is in parallel, so it's fairly easy. 1 over R parallel is equal to 1 over 5 plus 1 over 2 plus 1 over 1. Find a lowest common denominator of 10, 2 plus 5 plus 10, and you'll end up with 17 over 10. Don't stop there. R parallel is equal to 1 over. So, in other words, you need to flip your answer, so it's 10 divided by 17, which turns out to be 0,59 ohms. Determine the potential difference across R1, so we're over here. We've got a series current, so it's fairly easy. V is equal to I times R. We've got a series current, which is 2, and your resistance of the 1 ohm resistor is 1, so you'll end up with 2 volts. Determine the potential difference across R2. Pretty much the same deal, except that instead of having a 1 ohm resistor, you now have a 4 ohm resistor, and you'll end up with 8 volts. What is the resistance then of R3? Well, you have got 2 volts over here, you've got 8 volts over here. The total voltage is 24, so you need to subtract 10 from there, which means that if I had a voltmeter over here, it would read 14 volts. So I need to say resistance is equal to potential difference over current, and the potential difference is going to be 24 minus 8 minus 2, which is equal to 14, over series current of 2, and I land up with 7 ohms. Taking a look at the current on the main branch here, first I'm going to need to work out the parallel network of resistors. 1 over R parallel is equal to 1 over 6 plus 1 over 3, which is equal to 3 over 6, but R parallel is therefore equal to 6 over 3, which is equal to 2 ohms. Now I have got the potential difference. Series current is equal to the total potential difference divided by the resistance. So that's 12 divided by 2, and I land up with 6 amps. Calculate the value of R4. So what I'm going to do is I'm going to work out the total resistance. R total is equal to the total potential difference. Remember, we're not talking about internal resistance here, so it's fine. Divided by the series current. And we had changed this in the test, to 20 volts, because otherwise it actually doesn't work. So it's going to be equal to 20 divided by the series current is 1, so I land up with 20 ohms altogether, and therefore R4 is going to be 20 minus 3 minus 3 minus 6, which is going to be equal to 8 ohms altogether. Calculate the value of R2. Now things start to get a little bit more tricky over here. First I'm going to find out what is my total resistance. So I'm going to say R parallel, or R total, because there's only the parallel network, is equal to V divided by I, which is equal to 9 divided by 4,5, and that turns out to be 2 ohms. I don't know R2. It's parallel, so I can't just go adding. It's 1 over x plus 1 over 3 is equal to 1 over 2. And now I solve for x. The way that I do that actually involves you being able to do maths. But if you can't, I'll try and go through it a little bit more slowly. Find a lowest common denominator of 6x on both sides. I then say 6 plus 2x. 2 goes into 6x 3x times. And I'm left with 6 is equal to x. Those cancel out, and I land up with x being equal to 6 ohms. Determine the equivalent resistance of the circuit below. It's quite important that you take a look at the fact that there's a parallel network and the other two are in series, and therefore you need to separate them accordingly. 1 over R parallel is equal to 1 over 8 plus 1 over 4. If I resolve that, get a lowest common denominator, you should be able to, at this stage of your life cycle, be able to get R parallel is equal to 2,67 ohms. Then I add it to the 6 and the 4 that are over there, and I land up with the total resistance of the circuit is equal to 6 plus 4 plus 2,67, and that is equal to 12,67 ohms. Taking a look at this diagram over here, calculate the current through the cell. So I'm first going to have to work out all of the resistance. So it's 1 over R parallel is equal to 1 over 1 plus 1 over 1, which is equal to 2. But don't forget, I have to flip it. R parallel is equal to 0,5 ohms. R total is going to be equal to 1,5 plus 2 plus 0,5, which is equal to 4 ohms altogether. And therefore my current strength is going to be equal to potential difference divided by resistance. Altogether my potential difference is 18. Altogether my resistance is 4, and I land up with 4,5 amps. Determine the potential difference across R4. So what if I put a voltmeter over there? What would its reading be? I can say V is equal to current strength times resistance. I've just worked out the current strength. My resistance is 1,5. And therefore it is 6,75 volts. And what current is flowing through R2? Well, I know what the total current is. It's 4,5. And these are splitting exactly evenly, okay, because it's 1 ohm, 1 ohm. So I can literally just take 4,5 and divide it by 2 and get 2,25 amps. Right, now we've got a battery. It's connected to that arrangement. The power dissipated in the 100 ohm resistor is 0,74 watts. That's probably going to help me to get a current. I can then work out an ammeter over here. And let's see what that turns out to be. Power is equal to I squared R. And the power was 0,74 squared. And the resistance was 100. And I land up with I being equal to 0,086 amps. Okay, that's probably going to be helpful in a minute. The resistance of the voltmeters are so high they don't count. Okay, what is the current? Oh, we've just worked that out. Fantastic. Calculate the reading on V2. Now, V2 is over a parallel network, which means that I would need to first work out what the resistance of the parallel network is. So 1 over R parallel is equal to 1 over 50 plus 1 over 50, and when I work that out, R parallel turns out to be 25 ohms. Let's reduce that now to 25 ohms, and this entire current goes through that 25 ohms. So V2 is equal to the series current times the parallel resistance, and that is equal to 0,086 multiplied by the series current of 25, and I land up with 2,14 volts. What is the reading on V1? Now V1 is not connected across the parallel network. V1 has got these two resistors in there as well, and it's actually connected across the terminals of the cells. So I am going to say that V1 is equal to, I need to work out the total resistance of the whole circuit, and that is going to be the parallel network plus the 100 plus the other 25. So all of these need to be included, and I land up with 150 ohms. Therefore, the potential difference across the whole circuit is current times resistance, 0,086. The resistance of the whole circuit is 150, and I get 12,9 volts. We've got this kettle, and it's got those markings. What are the resistance? I know that power is equal to V squared divided by R, which means that I can say power is 1,200. V squared is 240 squared divided by R, and R, when I resolve it out, turns out to be equal to 48 ohms. If the kettle takes 5 minutes to boil water, calculate the amount of energy transferred by the kettle. Energy transferred is work done. Work done is power times time. The power is 1,200. The time is 5 times 60, which is 300, and I land up with 360,000 joules of energy transferred. Electric eels have got cells from their head to their tail. When the cells are activated by a nerve impulse, you get a potential difference. The potential difference is about 600 volts. What is meant by a potential difference of 600 volts? It means that 600 joules of energy is transferred to each coulomb of charge. They're just checking that you understand what a volt is. How much energy is transferred when an electron is moved through a potential difference of 600 volts? And you can find the charge of an electron on the information sheet. So we know the following. Work done, energy transferred, is equal to potential difference times charge, because potential difference is equal to work done divided by charge. I've got a potential difference of 600. I know the charge on one electron off my information sheet is 1,6 times 10 to the negative 19 coulombs, and therefore I get 9,6 times 10 to the negative 17 joules is transferred.